Nvidia is one of the most valuable companies in the world because of the GPUs it sells, and so it's useful to understand how far Nvidia is ahead of its competition. Now, there are many providers such as Intel with their Gaudi offering. There's also AMD. There's Amazon who has Trainium. But today I want to focus on Google's TPU offering, specifically the V6E generation. I'm going to do a comparison between that and running the H100 and the H200. I'll look at the throughput performance, time to first token, and also some cost comparisons. Before I show you the results, I want to explain how I'm setting up this benchmarking. First of all, I'll talk a little bit about these three types of hardware, 2 Nvidia and 1 Google. Then I'll talk about how I set up the benchmarking, the prices I assume per hour. I want to talk a bit about tensor-parallel versus pipeline parallel because this is important when it comes to thinking about the time to the first token. I'll then explain how to test out GPUs, namely Nvidia GPUs, how to test out TPUs, and last of all, show you some results and give some commentary. Now, I've set up this chat here with ChatGPT. I'll put a link to it in the description. And I've done a little comparison here on screen between the three types of hardware. So first of all, we have the Nvidia H100, the H200, and then the TPU, the V6E edition. Now, first looking at VRAM, which is the memory per unit, we've got 80 gigabytes for the SXM 100. We've got 141 for the H200, so quite a bit bigger. And for the V6E, it's just 32. So Google's hardware, at least at the latest generation, and there is a newer V7 generation that will have much higher VRAM. It's currently quite small compared to the Nvidia offerings. Now, the Nvidia B200, which I'll hopefully look at in an upcoming video, has got even more VRAM. It's got 180 gigabytes. So you can see this is increasing to allow model providers to fit larger models on fewer GPUs. The next parameter to look at here is the high bandwidth memory speed. This is critical in moving the weights from the VRAM into the internal part of the GPU or TPU that does the calculations. And here you can see that NVIDIA's units, they are certainly faster in bringing information into the inner cores where calculations occur. The H200 is a little bit faster than the H100, maybe 30 to 40%, whereas Google's V6E is about half of the speed of the H100. The next thing to look at is the interconnect speed between GPUs. Often to fit large models, you need to put multiple GPUs together. You can put them together in parallel, or you can put them together kind of in series. We'll talk about that later. It's tensor parallel and pipeline parallel. You can see also a speed here. So this is gigabytes per second. And the speed for the H100 and H200 is the same in this case, but it's about half for the V6E. So if you have communication between your devices, it's going to be faster in the case of Nvidia than in the case of Google. Now, the next unit here to look at is the flops. This is the floating point operations per second, and I've compared them here on the basis of 16-bit non-sparse flops. Nvidia reports their flops on a sparse basis, which is basically just multiplying by 2. But I want to normalize to compare. And interestingly, these units have got similar flops. And that's actually particularly high in the Google case, because if you look at it on a normalized basis per unit of VRAM, Google then has a lot of compute. So Google has got a lot of compute for the high bandwidth memory speed and a lot of compute for the VRAM. And probably that means that in quite a few cases, the TPUs are going to be limited in their throughput by how fast the weights can be read into the inner part of the TPU, rather than just the computing or the computing crunch rate, which is very high on the TPUs here. Okay, so when I do a comparison, I'm going to run a Gemma 27B model, and I'll show you the table for that in a moment. But I'm going to run it on the following configurations. I'll run it on 8 of these V6E units. So that's 8 times 32 is 256. I'll run it on 1 H200 and 2 H100s. So I'm trying to get very roughly the same amount of VRAM in each case and just run that comparison. Now, when I look at the cost comparison, I'm going to take the cost of the exact numbers of GPUs or TPUs that I use and then divide by the throughput in tokens, so we can have kind of a fair comparison of cost per million input plus output tokens. If you didn't catch all I said, I'm going to go through it now in a bit more detail. So let's take a look. First of all, at the model we're going to choose. It's the Gemma 3 27B model. This is a relatively small to medium-sized model. In the future, I'll run again maybe one of these videos with a larger mixture of experts, which will do a better job of testing the interconnects between GPUs. But since we are using 8 TPUs and we're using 2 H100s, you'll get some sense of that baked into the performance we see today. I'm going to run these all in 16 bits. Normally I would run them in FP8, floating point 8, if I was going to run on Nvidia because they support that. But the TPUs, they don't support a dynamic FP8 format for the weights. In principle, they can upcast to 16 bits from certain 8-bit precisions, but it seems that they can't from the precision I was giving. So I'm going to run everything at 16 bits, which means that you do need twice the memory, twice the VRAM that you would need compared to just running in 8 bits. Now, the model itself in 16 bits is somewhere around 50, 60 gigabytes. So it fits easily within 2 H100s, that's 160 gigabytes, 1 H200, which is 141, or 16, it's not 16, it's 8, sorry about that. So it should be 8 multiplied by 32, which is 256 gigabytes of VRAM. So it's true that I am allowing quite a bit more VRAM in the case of Google, and I'm allowing quite a bit more compute, just because there's quite a bit of compute per TPU. But I will normalize per throughput when it comes to cost, so it should be a somewhat fair comparison. Now, for benchmarking, I'm going to run the same library on all of the hardware, so it'll be vLLM. Now, just because it's the same library still doesn't mean the software is of the same quality or completeness in each case, because vLLM may not be using kernels that are available on Nvidia when it's running on the TPUs, and so you can have differences in performance there. So really this performance is a reflection of both the hardware and also the state of the software integration between this inference library and the underlying kernels that are offered by the TPUs and by Nvidia. For benchmarking, the tool I'm going to use to send requests is going to be llm-perf. I'll use 5,000 input tokens with a variance of plus or minus 50. I'll use 1,000 output tokens with a variance of 50. And I'm going to test with concurrencies of 1, 8, and 64. That's how many simultaneous requests we're going to be handling at a time. And I'm going to compare the time to the first token, the time per output token per request. This is the rate at which the output tokens are generated per user request. And then the throughput in output tokens per second across all user requests, which will ultimately be used to calculate the cost per output tokens. Now, for comparing these in terms of price, here's what I'm assuming for prices. I'm assuming a H100 at $3.99 per hour. This is an on-demand price. If you get a spot price where you can be interrupted, you can get it much lower. But in most cases, you do not want to be interrupted. So I'm taking the demand pricing here from RunPod. I think it's actually a little bit higher if you go through AWS, but you could probably find lower as well, maybe on platforms like SF Compute. For the H200, I'm assuming $3.99. Of course, the H100 is multiplied by 2 because there's 2 of those. So the rental cost of that node, it's a node of 2, is going to be about $6 an hour. And for the V6-8, for 8 of the V6Es, I'm assuming $270, which is the price Google publishes for on-demand. So that's 8 times this, is $21.60 per hour. And then my price metric or cost metric is going to be my dollars per hour, and then divided by the number of tokens produced per hour, which I just showed you here, the throughput in output tokens per second, then multiplied by 3,600 to get that to hours. Okay, so before I show you how to actually inference with these libraries and how to get access to TPUs and GPUs, let me just talk about tensor-parallel versus pipeline parallel. This is more important if we were talking about bigger models, but it's still relevant here. These are 2 ways that you can split a model across GPUs or TPUs. So let's start off by imagining a very simple transformer model with just 4 layers. Typically, they would have more, like 48, 36, 96. But here, let's just consider 4. Each layer's got attention matrices and multi-layer perceptron matrices. So the tokens will come in, there's multiplication, you pass that information on, multiplication, and pass it on, and then you finally get the output token prediction. You would feed that output token back around and auto-regressively generate next new tokens here. So this is your basic or a very basic model. And something that that's going to ground our analysis is that the VRAM or the memory that's required to fit this model here is not just going to be the model weights, which refers to the weights used in the attention and MLP matrices. You also need enough memory for what's called KV cache. And KV cache is basically storing the history of calculations for earlier tokens. So we're not just inputting one token each time, we've got a full history, and there will be some computation for each of those tokens in the history that will be stored, so we don't need to recompute it when we autoregressively come around and pass in the next decoded token. So that KV cache requires storage in the VRAM on top of the model weights. And how that's stored will depend on whether we parallelize or serialize the GPUs. So let's start with pipeline parallel. Let's assume we've two GPUs here. They could be TPUs either. And in pipeline parallel, you just split the model layers across the GPUs. So here, if we've 4 layers, we've pipeline parallel of 2. We're going to put the last 2 layers on the second GPU and the first layers on the first GPU. And when you compute forward, you've input tokens come in, you have to crunch everything in the first GPU, and the second GPU is just waiting. And then you crunch in the second GPU. Now, once things get up and running, you're going to be continuously producing tokens from the second GPU, but the time to your first token is going to be delayed because you've got to pass it through multiple GPUs in series. So you'll see later, time to first token is slower if you do pipeline parallel. But the benefit here with pipeline parallel is that you're able to split the model weights across GPUs. So if you have a model, you can fit it in 2 GPUs. You only need to fit half of the model in each GPU. And furthermore, the KV cache, so the history for each tokens, you can also split that by layers. So any history associated with layer 2, you just have to keep on GPU 1. Any history associated with layer 3, you keep on GPU 2. Any history associated with layer 4, you keep on GPU 2. So you can just divide pretty much in half the weights and divide in half where the KV cache gets stored. Now, it's actually more common to use tensor-parallel, and the reason is because you don't have that delay of having to pass the tokens to the next GPU or even subsequent if you've got multiple pipeline parallel stages. So in tensor parallel, you break the matrices within these layers in half, essentially, if it's tensor parallel 2, and you will then need communication at each layer. So each layer will need communication across the GPUs or TPUs so that you are able to assemble what you have calculated before moving on to the next layer. And this is quite a bit more communication than is involved in pipeline parallel because you only need to pass information at the interface of the layers here, or the interface rather, of both layers and GPUs. Now, luckily the communication, and I talked earlier about the communication bandwidth between GPUs, this is very high in Nvidia GPUs, it's relatively high in TPUs as well. And so this doesn't end up being that much of a bottleneck. And so tensor parallel works quite well. But one thing about tensor parallel is that you do need to store the entire KV cache within each of the within each of the GPUs. So you're now no longer able to split them according to layers. You basically have to store all of the KV cache. And this means that much more of each GPU is going to be taken up by just storing KV cache, which will leave less room for storing weights, which means that you're going to need to have more TPUs or more GPUs if you do tensor parallel than if you do pipeline parallel. But tensor parallel is faster because you don't have to have this delay to the first token here. So basically by doing the pipeline parallel, it allows you to fit more. You can ultimately hit a higher request throughput just because you will run out of KV cache. You will run out of memory later, but it's going to slow down your time to first token. So in summary here, in Nvidia and Trainium GPUs, TPUs, the interlink bandwidth is high. So you can basically do tensor parallel without much of a penalty, particularly at lower batch sizes. Sometimes at higher batch sizes, it becomes common to use maybe pipeline parallel of 2, maybe 4, so that you can get a bit more out of the memory. The problem with pipeline parallel is the longer time to the first token because of multiple stages. And the problems with tensor parallel are storing the KV cache. And this is particularly a problem for TPUs that currently have only 32 gigabytes of VRAM, because if the VRAM per GPU is quite small and you're doing tensor parallel, you're already taking up a lot of your VRAM just with the KV cache, and that's forcing you to then use a lot of connected units within the same node in order to fit larger models. And this is part of the reason why the next generation, I think it's V7e from Google, will have much larger VRAM, more on par or closer to what the Nvidia H200, H100 and B200 have. Okay, so if you want to test NVIDIA or TPUs, NVIDIA, you can test them in very many places. I'm going to test them in RunPod. You could test them on Vast AI, on AWS, on SF Compute, on Azure, on maybe even Google Cloud. TPUs, you can only test on Google Cloud. If you have a business account, the default, I think, is an allowance for 16 of these. So you can do 16, -16. But actually, I wasn't able to find 16 available. I was only able to start up a node with 8. So this is partly why I've tested a model that's not that big, because I wasn't able to get access to v6e-16. For -32, you need to request allowance, which is kind of difficult to do via Google Cloud. I think you have to go into support, and you're not eligible for it unless you've spent a certain amount before. So it's not clear to me how I get access to larger ones, but I'm going to try. Now, later on in future videos, I'm hoping to test out the B200 to test out on larger models, although I need to get access to the V16 at least to be able to do that. Probably even the V32, V6E32, because I have to run in 16 bits. And that would be necessary to run Llama 4 Scout. I'd need 32 because I'm forced to run in 16 bits. And also then I'm interested in checking out Trainium, so I'm working on getting access to that. All right, so let's talk about how you run inference here. And there are 2 things needed per setup. So you need to figure out, how do I run the GPU? Then how do I run the inference library on that GPU? How do I run the TPU? And how do I run the inference library on that? All of the scripts I've got in the advanced inference repository, which you can purchase annual or lifetime access to on trellis.com. I've cloned that in to Windsurf. And you'll see in the benchmarking folder, there is a README here that describes how to go through all of this. Now, the first thing I'm going to do is I'll just quickly set up a RunPod GPU. I'm going to go to this public repo that has one-click templates for starting up a RunPod instance. And I'm going to start up the Gemma 3 template that I mentioned. I'm not going to start up, this is SGLang. I'm going to start up vLLM. The reason I'm using vLLM is because it's supported on Trainium on the Google TPUs, whereas SGLang is not just yet. So I'm going to start Gemma 3 in 16 bits. If I click that link, and you might have to create an account, it's an affiliate link, by the way, you can then select a GPU to start up on. Now, I'm going to start with, I'm just going to run the H200 here, and I'll say Gemma 3 27B. If you are going to work with the H100 and you want 2 GPUs, you would put in tensor-parallel size and then put in 2. But we can easily just run on one of these, and you need 75 gigabytes should be fine. So I'll start up this unit here. Okay, so next I'm going to, while that's starting, I'm going to set up my benchmarking library. And for that, I'm going to clone llm-perf, and I'm going to install within that directory. So I'll just paste all of this here, and everything is installed. And now I'm actually ready to either run a benchmark directly, or I've set up a benchmarking script that automatically runs the batch sizes of 1.8 and 64. And to run that, I need to specify, first of all, the hardware, which here will be 1 by H200. And I'm actually going to just give it a test flag here. vLLM, I need to put in the model name and the pod ID here. So I'll go back, get my pod ID, paste it in. And the model name I want to run is actually Gemma. And I'm going to run it from the Unsloth organization on Hugging Face because it does not require an API token to access it. So this is how I'm going to run the benchmark script. And all I'm waiting on now is for this to start up. So I'll be waiting on the logs. You can see that it's firing up right now. Okay. So while this is firing up, and before I run inference, I'll just explain briefly how the TPUs can be set up. So for TPUs, there is a more elaborate setup, and it's in the TPU folder here. I'll take you through just some of the high-level steps so you can understand what's happening. But the very first thing you're going to do is set up an environment variables file. And I'll show you the sample environment variables file here, just so you can see a few things we have to set. We need a Hugging Face token to access the model. That's probably not critical because we're using a model that's not gated. you need to give your TPU a name. So for example, you might give it Gemma TPU VM. You need to pick a Google Cloud zone. Now there are only 4 zones where there are 16 units, TPU units available, although I anyway can't get access there. And I think you can access the 8 units of a TPU, a node with 8 in US East 5A. If you just leave this to your project ID, it'll use your default project from G-Cloud. TP is the tensor-parallel value to use. We're going to run in tensor-parallel with a value of 8. This here, the TPU type, it's actually going to set the folder where the results will be saved, but it's also going to specify with this first part here, the last part will be ripped off. The first pass here will set, what TPU you are requesting from Google. So if we go back to the README here in TPU, we can keep working down. The very first thing we're going to do is run the create TPU script. So this will send a request to Google Cloud to check if there's availability and then start an on-demand TPU. Then we're going to have to set up vLLM. We're going to use a Docker image. There's a Docker image available for vLLM for TPUs. So that's nice. And once that is up and running, we're then able to create a script to serve the model. This actually doesn't serve the model. It creates a script to serve the model. And then we need to have that script available on the machine. So we need to be inside the TPUs and run the script in order to serve the model. So what we do is first make sure we have access to the environment variables. Then we'll SSH in to Google Cloud. And once we've SSH'd in, we're going to copy this serve on TPU script that will have been created by the serve model script. And that will be copied up onto the cloud so that then we're able to run the serve on TPU script on the cloud. It's actually going to print the commands out when we get to that point. So we'll run this here to give permission to run the script and then run that TPU script. Also, we want to set up port forwarding. So we want to forward the port on the cloud to our local instance. So we're actually able to send our benchmarking requests up from locally. So that's why we will run this port forwarding script here. So I'm just going to very quickly show you some of the highlights here. This is the create GPU script. Essentially, we're calling Google Cloud. We're creating a TPU with the given name, given accelerator type, which is going to be based on the TPU type that we set in the environment variables. We'll have a project name, a zone, and then this version is required if we want to run the V6E. So this is creating our TPU. Then we're going to set up vLLM. Again, you'll see that you'll check that the TPU actually exists, and then we'll start up the Docker container. And you can see here we're starting up the nightly version of the vLLM TPU Docker container. Once that's done, we will serve the model. And as I said, this doesn't actually serve the model. It creates a script. So it's going to create this script here that will export our Hugging Face token in case that's needed to access the model. And then it's going to run the serve command here for Google Gemma 3 27B. IT is the instruct version. So it's going to run it with this model length, this tensor parallel, max number of sequences 128. And yeah, that's pretty much it. And once that's done, we're going to make sure that we have port forwarding set up. So this short script here is going to set up port forwarding to the local port of the remote. And then we'll be in a position to copy up our files, and then we'll be able to run the benchmark local. So you'll see here, we're running a benchmark. We're defining the directory for the results, and we'll be hitting this local host address here, to which we have already forwarded what's happening. Now, I can just show you very quickly how this gets started, but I'm not going to show you the full startup because actually vLLM goes through a ton of tests to build, I think, graphs. So the startup, even for a model that's not that big, it takes at least maybe 10 to 15 minutes. There are a lot of checks within the vLLM TPU library that just aren't there for the CUDA library. So if I wanted to get this going, let's see, I could adjust my environment variables file. And by the way, I've already scratched this HF token, so it shouldn't really matter. But I would want to run this V6E, and then I would run create tpu.sh. And by the way, I need to be within the TPU folder. And then I would run create TPU, and it should load the environment variables. And yeah, it's going to request. And it looks like it's requesting a V6E 16, which is not what we want actually. I should have set this to 8. And so this is probably going to fail because I don't actually have access. Well, I do have access, but there isn't availability of the 16 V6Es. And by the way, the reason why why this didn't update to what I've got shown in this file is because I need to resource my environment variables. So I should run the source command that's here in the README. If I just go to source, yeah, I need to source my setup so that I pull the latest environment variables into my environment and then run, and then it will try to find a V6E8 to run as a TPU. Okay, so I'll leave that to those who want to get access to the repo. And for now, I'll just show you benchmarking on the runpod instance. So here we have over in runpod, if we check the pods, we are up and running. So if we check the logs here, we should see that the application startup is complete. We've got the pod ID. The only other thing we need is the model name, but we already have that. So if I go back to the benchmarking file, I should be able to just run this test here. And yeah, I'm saving the results in just a quick test folder. So if I copy that and I go to a terminal here, I need to move back into the benchmarking folder. And let me just check. Need to check that I'm in the right folder here. Benchmark, I need to CD into llm-perf and then run here. And now it's going to start up and start benchmarking with one concurrent request. Then it's going to move to 8, and then it's going to move to 64 requests. And in the meantime, you should start to see over on runpod, the GPU is going to be busy. And we should start to see some logs here as we start to hit the endpoint. We'll just wait for one request to come back. Okay, so you can see here, we have streaming of text and we're generating. So we're starting to gather data. And all of this then is going to be saved within the benchmark results folder. So you can check out here within vLLM, we've got the test results that will be populated. But I've run this earlier. So I've collected for Gemma 3 27B results for concurrency 1864, the same for the 2 by H100 SXM, and the same for the 1 by H200 SXM. And I just notice here that my folder should be named a little bit differently, but we do have all these results. And with that, I should be able to now graph a copy of the results in order to show you what performance we have. So I can just run generate graphs. And I've got a sample script here where I can decide to run a comparison of this model here with vLLM for these different architectures or these different hardware sets. And I need to be in the benchmarking folder for this. So just CD back, run that command, and all of my graphs should be saved up now to the benchmark graphs folder, which is here. And now we can take a look at some of the results. So the first one we'll take a look at is the time to first token. And here you can see that of the three, the lowest time to first token is the TPU. Now, when we get up to concurrency of 64, we have a very slow time to first token. And that's because we're probably towards the limit of the batch size that we can support on these two given hardwares. Keep in mind that the TPU, we've got more VRAM available overall. So that's probably helping us in part to run larger batch sizes. But comparing at the other batch sizes of 1 and 8, you can see time to first token of above about 0.9 seconds for the 1 by H200 and the 2 by H100, whereas for the V6E8, we've got below 0.8, so about 0.76 and 0.79 in the case of concurrency 1 and 8. The next thing to look at is request output TPS. So here you can see that obviously the speed of the output tokens goes down as we go to larger batch sizes. Probably this batch size of 64 is unusable. It's too slow of a token generation rate. So the realistic batch size is somewhere between maybe 8 and 64, probably closer to 8. And you can also see how the token production rate is pretty similar in all three cases. The highest token production speed is in the H100, and you can see that the 8 V6Es are a tiny bit faster than just one H200. Next, we can look at token throughput. This is the total rate across all requests, the rate of token generation. And you can see here the highest throughput is the 2x H100s, and that's higher than both one H200 or 8 of the V6Es. Now, of course, the most important thing is when you pull all that together for cost, where do things land? And here you can see it. When we go to batch size 8, on the 1x H200, we've got about 57 cents per token. We've got 74 cents on the 2x H100s, and we've got 2.85 on the concurrency 8 with the 8 TPUs. Now, I would caution that these numbers, I'm taking probably fairly high values for the rental cost per hour. And if Google is going to run their TPUs, the effective rental cost per hour is probably quite a lot lower. And it's the same when you're looking at OpenAI or Anthropic serving on Nvidia hardware. They're going to have probably quite a bit lower serving costs for rental or effective per hour ownership rate. So it's more important to look at the relative values here and consider on a relative basis how these different hardwares compare. And the main conclusion is that, well, the TPUs definitely look quite a bit more expensive, maybe by a factor of roughly 5. When you're at the low batch size, there's maybe a little bit less of a gap between 3.5 to 4. But here at the batch size of 8, you've got 74 cents versus 2.85, and you're actually getting even lower cost with the H200 of 57 cents. And that's just because for, roughly similar VRAM, although the TPUs have got more VRAM in this 8 unit configuration, because you have to pay for 8 of these TPUs, that's $270 per TPU per hour times 8. And so the cost is quite a lot higher, whereas you're only paying for one H200 here or 2 H100s here. So I was quite interested in seeing this result. I didn't really know where it would come out, but certainly doesn't seem like the TPUs are coming out as particularly cost effective with the vLLM library. Now, you'd have to assume that Google, when they run inference, are using their own libraries and are optimizing this far more than vLLM. And vLLM is nearly always run on Nvidia, so it's probably a lot more optimized for Nvidia than it is for the TPU hardware. But if you consider a developer who wants to use hardware, you can see how it's going to be much easier and much more cost effective to be running on Nvidia hardware than to be running on TPU hardware. I think it's also notable that the TPUs have got very high compute rates, so they have very high compute capacity. They have a bit lower speeds in terms of moving the weights to the inner part of the TPU than the Nvidia GPUs, so that's a disadvantage. The interconnect speed is a bit of a disadvantage, but given they have such high ability to do compute, it just shows you that the compute utilization is probably not very good, and maybe that indicates room for improvement that the Google libraries already have perhaps, or maybe it just highlights the fact that the software in general, at least the open source software, is far more performant or developed for the Nvidia hardware than for the TPUs. All right, folks, that's my first benchmarking of TPUs versus GPUs. I think there's a lot of room for improvement, so let me know in the comments if you have suggestions on better parameter sets to run. I also will consider running a little private workshop to expand a bit more on this. If folks are interested, you can find a link below where you can sign up to be notified when I announce a date for that. Cheers.